Welcome to section 4.2, second derivatives and graphs. Today's goal is to use our second derivative to analyze our graphs. So, for our notation on our second derivative, if our function y equals f of x, then the second derivative of f, provided that it exists, is f double prime of x, or the derivative with respect to x of f prime. So what we'll do is we'll use all of our same derivative rules, and this time we're taking the derivative of the first derivative, which gives us our second derivative. Concavity is something that we'll be looking at now. The graph of a function is considered concave up in an interval if its first derivative f prime is increasing, and it's concave down on the interval if the first derivative is decreasing. So for our interval from a to b, basically when we find our second derivative and it's positive, that gives us the information to tell that our first derivative is increasing, and so as a result our original function is concave up. If our second derivative is negative, that means that our first derivative was decreasing, which means our function is concave down. So much like our first derivative tells us where the graph was increasing and decreasing, our second derivative will tell us where it's concave up and concave down. Inflection points will be where our function is going from concave up to concave down or concave down to concave up. So these will work much like our critical values. In this case, it will be telling us where our concavity is changing. So our function y equals f of x is continuous on AB and has an inflection point at x equals c, some value of x. Then either f double prime of that value c is 0 or f double prime does not exist. So those are the cases that we'll be looking for to determine an inflection point in that area. The procedure that we'll be using, graphing strategy. So step 1, we'll analyze f of x, finding the domain, the intercepts. Step 2, we'll take the derivative and analyze that, which will give us partition numbers, critical values, and determine the local extrema, so our maximums and our minimums. Step 3, we will take the second derivative and analyze that, which will give us partition numbers for our second derivative, and then we can determine where is it concave up and concave down. Having all of that information will give us the best sketch of our function f. Okay, so given the function f of x equals 7x to the fourth minus 11x cubed minus 15x plus 3, find the second derivative, f double prime of x. So we have to do this in steps. The first step will be finding first derivative, f prime. So the derivative of 7x to the fourth, 28x cubed, derivative of negative 11x squared minus 22x, derivative of negative 15x, negative 15, and the derivative of 3 is 0. Next, we'll take the derivative again, which will give us our second derivative, f double prime of x. So the derivative of 28x cubed, 56x squared. The derivative of negative 22x, negative 22. Derivative of 15, 0. So this is our second derivative. Given the function f of x equals 4x to the fifth plus 12x to the 18 fifths minus 19, find f double prime. We'll use the same process. First we find f prime, 4x to the 5th. Derivative is going to be 20x to the 4th. 12x to the 18/5. So we still use our power rule. 12 times 18 over 5 will give us 216/5. We subtract 18/5 minus 5/5 will be 13/5. Minus 19, the derivative of 19 is 0. Okay, second derivative, we take the derivative again. Derivative of 20x to the 4th will be 80x cubed. And the derivative of 216/5 x to the 13/5. So we use our power rule, 216/5 times 13/5. We will have 2,808 25ths x. Then we subtract 1. 13/5 minus 5/5 will give us to the 8/5. So don't be frightened if we see a rational exponent. As long as it's just x to a power, we can still use the power rule. Given the function f of x equals 2x cubed minus 18x squared plus 7x minus 11, find the x and y coordinates of all inflection points. Okay, so our inflection points are found by setting our second derivative equal to 0. So let's find our second derivative. Our first derivative will be 2x cubed, so we'll have 6x squared. 18x squared, so we'll have 36x. And 7x will have 7. Derivative of 11 is 0. From here we can find our second derivative. Derivative of 6x squared will be 12x, and the derivative of negative 36x will be negative 36. Derivative of 7 is 0. Now our inflection points are going to be where that second derivative is equal to 0. So we're going to take our second derivative, set it equal to 0, and see where are those inflection points at. So we have 0 equals 12x minus 36. 12x equals 36. So x equals 3 if we divide. Now we're looking for a point in this case, so I have the x value. I want to know the y value that is associated with it. So I'm just quickly going to plug this into the function and see what's my y value. 2 times 3 cubed minus 18 times 3 squared plus 7 times 3 minus 11. So this will give us 54 minus 162 plus 21 minus 11, so negative 98. So this point, inflection point, is at 3, negative 98. We'll keep that information handy. So what we want to check now is that it actually does change at this point. Okay, so the second derivative is going to tell us our information. Since 3 is the point that we're looking at, what I'm going to do, just like before, is look on both sides of 3. So I'm going to look at 2 and I'm going to look at 4. So my second derivative, if I plug in 2, then I'll have 12 times 2 minus 36. So that will give us negative 12. So it's negative on this side of the 3. If we have the second derivative of 4, that'll be 12 times 4 minus 36. That will give us positive 12. So on this side, it's positive. So this is telling us it's concave down and then concave up. And since it goes from concave down to concave up, 3 is in fact an inflection point. And so we can say the point 3, negative 98 is an inflection point. Now if we had checked it and it was concave down to concave down, it's not changing concavity, so it wouldn't be considered our inflection point in that example. In problems 4 through 6, for the functions given, find the intervals on which the function is concave up, the intervals on which the function is concave down, and the inflection points. Our function is going to be f of x equals 2x to the 4th minus 48x squared. So the first thing we want to do is find our second derivative, so that way we know what numbers are our partition numbers. So our first derivative will be derivative of 2x to the 4th, so we have 8x cubed. The derivative of 48x squared, so we have 96x. Our second derivative of 8x cubed, 24x squared. Derivative of 96x, 96. Now we set this equal to 0 to find our inflection points. So we've got 24x squared equals 96. X squared equals 4. And so x is going to be positive or negative 2. So we're looking around negative 2 and positive 2. So what we could do here is check negative 4, positive 4, and 0. These are values on either side of these inflection points that we're looking at, the partition numbers, I suppose. We haven't determined if they're inflection points just yet. Okay, so now we'll test negative 4. So our second derivative, f double prime of negative 4, gives us 24 times negative 4 squared minus 96. And so we'll have 24 times 16 minus 96, 384 minus 96, or 288 positive. Our second derivative of 0 is 24 times 0 squared minus 96, negative 96. So negative. And our second derivative at positive 4, 24 times 4 squared minus 96, 24 times 16. This is going to take us to the same 288 of positive number. Okay, so now let's answer some questions. The interval on which the function is concave up. Okay, so where is it positive? It's positive from negative infinity up to -2, and then again it's positive from +2 all the way through to positive infinity. So the function is concave up on the interval negative infinity to -2 and +2 to positive infinity. The function is concave down on the interval from -2 to +2. And the inflection points are going to be both, because we can see it's changing from concave up to concave down to concave up. So these do become our inflection points. We just need to determine what are these points. So what I'm going to do is I'm going to plug in to my function f of -2 to find out what's the y value at -2. So we'll do 2 times -2 to the 4th minus 48 times -2 squared. 48. This will give us, let's see, -2, -160. So the inflection points are -2, -160. If we plug in +2, since they have even exponents, it will be the same. -160, so, and 2, -160. Okay. F of x equals 3x cubed minus 11x. We have a typo here. Minus 18x squared plus 4x minus 10. Okay, so just as before, we want to find our second derivative and develop our partition numbers. F prime of x will give us 9x squared minus 36x plus 4. Our second derivative, 18x minus 36. Now we set our second derivative equal to 0. So 18x equals 36, x equals 2. So we'll look on either side of 2. Let's look at 0, and we'll go 4. Our second derivative at 0 will give us 18 times 0 minus 36, so negative 36, concave down. Our second derivative at 4 will give us 18 times 4 minus 36. 72 minus 36 is 36, positive, concave up. So the function is concave up on the interval from 2 to positive infinity. the function is concave down on the interval from -infinity to 2. And the inflection point is at 2, let's see, f of 2, 3 times 2 cubed minus 18 times 2 squared plus 4 times 2 minus 10. 8, 24 is -50. So our inflection point is at 2, -50. Okay. F of x equals 16 e to the x minus 2 e to the 2x. Our first derivative is going to be 16 e to the x is itself, 2 e to the 2x, so we have 2 e to the 2x, chain rule times 2, so we have 4 e to the 2x. And our second derivative, 16 e to the x, and then we've got 4 e to the 2x, chain rule times 2, so we've got 8 e to the 2x. We set our second derivative equal to 0. And we can do 16 e to the x equals 8 e to the 2x. If I divide by 8 e to the x, then we'll be left with 2 equals e to the x. In this case, when we're solving an e to the x, we will take the natural log of both sides. So that way we have natural log of 2 is equal to x. So this is going to be the value that we're looking around. A number less than natural log of 2 could be 0, and a number greater than natural log of 2 can be 2. To determine this, just put natural log of 2 in your calculator, and then it'll give you the decimal so that you'll be able to determine numbers greater than and less than. So our second derivative at 0, 16 e to the 0 minus 8 e to the 2 times 0. So we have e to the 0 is going to be 1. 16 minus 8 is going to give us 8. Positive, concave up. Our second derivative at 2 is going to be 16e squared minus 8e to the 2 times 2. 16e squared minus 8e to the 4th. In our calculator, this will give us about negative 318.56. So this is a negative number, so we have concave down. So it is an inflection point. function is concave up on the interval, or concave up from negative infinity to natural log of 2. The function is concave down from natural log of 2 to positive infinity. And then our inflection point let's find out what our value is. So we've got our function f of x at natural log of 2 is going to be 16 e to the natural log of 2 minus 2 e to the 2 natural log of 2. And so we've got natural log 2 and 24. Okay. In problems 7 through 9, apply the 4-step graphing procedure and sketch the graph of the following functions. F of x equals x plus 2 times x squared minus x plus 4. So, our first step, we are going to analyze our function. Remember, this is finding the domain and the intercepts. So, our domain of this, we don't have any restrictions on our x, so our domain is all real numbers. And to find our intercepts, we set the opposite variable to 0. So for our y-intercept, we make x equals 0. So we have f of 0 is going to be 0 plus 2 times 0 squared minus 0 plus 4. So we'll have 2 times 4. There's another typo here. This is a minus 4. Negative 8. So our y-intercept is 0, negative 8. And our x-intercept, we're making y 0. So we have x plus 2 times x squared minus x minus 4, which means x plus 2 equals 0, x equals negative 2. And then x squared minus x minus 4 equals 0. So for this one, we'll need our quadratic formula. So we'll have x equal negative b plus or minus square root b squared minus 4ac all over 2a. So this will give us b negative negative 1. So we have 1 plus or minus square root negative 1 squared minus 4 times 1 times negative 4 all over 2 times 1. This will give us 1 plus or minus root 17 over 2. Okay, so our x-intercept, we have 3, we have negative 2, 0, we have 1 plus root 17 over 2 and 0 minus root 17 over 2 of 0. So we've gathered our domain, our y-intercept, and our x-intercepts here. Step 2, analyze our first derivative. So let's take the derivative. F prime will be, we have the first times the derivative of the second, 2x minus 1, plus the second times the derivative of the first. Okay, so this will give us 2x squared plus 3x minus 2 plus x squared minus x minus 4. Setting this equal to 0, 3x squared plus 2x minus 6. And again, we'll use our quadratic formula. So we have negative b plus or minus square root b squared minus 4ac all over 2a. We'll have negative 2 plus or minus square root 2 squared minus 4 times 3 times negative 6 over 2 times 3. So we'll have negative 1 plus or minus root 19 over 3. So our partition numbers will be negative 1 minus root 19 over 3 and negative 1 plus root 19 over 3. And if we put that in our calculator and get the decimal form, we can choose numbers around these values. So I'll go negative 2, 0, positive 2 for mine. And we'll see what happens. F prime at negative 2 will give us 3 times negative 2 squared plus 2 times negative 2 minus 6. 3 times 4 minus 4 minus 6, 2. This is positive, so we have increasing. Our derivative at 0, 3 times 0 squared plus 2 times 0 minus 6 gives us negative 6, so it's negative, so decreasing. and our derivative at 2, 3 times 2 squared plus 2 times 2 minus 6, 3 times 4 plus 4 minus 6 will be 10, positive, increasing. So we have an increasing, decreasing, increasing, which tells us this value, -1 minus root 19 over 3 is going to be local max. -1 plus root 19 over 3 is going to be a local min. We can also make a note that it's increasing from -infinity to this max value, -1 minus root 19 over 3, decreasing from -1 minus root 19 over 3 to -1 plus root 19 over 3, and increasing again from -1 plus root 19 over 3 to positive infinity. So the information we've collected here, we have a max at this value, a min at this value. We know where it's increasing, where it's decreasing, where it's increasing again. All right, let's continue. Step 3. We'll analyze our second derivative. So, going from our first derivative to our second derivative, derivative of 3x squared will be 6x. Derivative of 2x will be 2. And we set this equal to 0. So we have 6x equals -2, x equals -1/3. So that's where we will look around. -1/3. Lower than that, let's look at -1. Higher than that, let's look at 0. Those are pretty easy numbers to work with. So our second derivative at -1 will be 6 -1 plus 2. So we'll have -4. So that tells us concave down. Our second derivative at 0, 6 times 0 plus 2 gives us 2. That's positive, so it's concave up. So it's concave down from -infinity to -1/3, concave up from -1/3 to positive infinity. And we have our inflection point. So the information we've gathered here is we have an inflection point at -1/3. It's concave down from -infinity up to that -1/3, and then it goes concave up. Now we can sketch our function. So let's start with our y-intercept is 0, -8. We'll put that down here. we will put our x-intercept, all three. So we have -2, 0. We have 1 plus root 17 over 2 and 1 minus root 17 over 2. And those values, let's get an idea. 1 plus root 17 over 2, 2.5. So that will be over here. 1 plus root 17 over 2. And 1 minus -1.5. So it's going to be really close to that one. Okay. Next, we know it's increasing up to this -1 minus root 19, and then decreasing, and then increasing. And we also know that it's concave down all the way until -1/3. So what this is telling us is we have this maximum, we are increasing, we hit our maximum, and then we are decreasing. And it says after that inflection point at -1/3, we go from concave down to concave up. So it's going to go to concave up, hit that point. We have our minimum at -1 plus 19 over 3, which is in between 0 and 2. So it's going to hit our minimum, and then it's going to come right back up. So I'm actually going to scoot this over. Because we're going to hit a minimum, and then we're going to come back up. And so our sketch will look something like this. And to be honest, after you sketch, I always double check by putting the function in the graphing calculator and making sure I was on the right track. Okay, f of x equals 5x to the 4th minus 10x cubed. Okay, step 1. Analyze our function f of x. So, what's our domain? We don't have any restrictions on what we can plug in for x. So our domain is all real numbers. Let's find our intercepts. So our y-intercept, we've got f of 0. 5 times 0 to the 4 minus 10 times 0 to the 3rd equals 0. So we've got a y-intercept of 0, 0. X-intercept 0 equals 5x to the 4th minus 10x cubed. Let's factor 5x cubed out. So we'll have x minus 2. So this will tell us 5x cubed equals 0, x has to be 0, x minus 2 equals 0, x has to be 2. So we have two x-intercepts, 0, 0, 0, and 2, 0. Okay, just to keep track of our information, we have our domain, we have our y-intercept, and we have x-intercepts. All right, step 2, analyze our derivative. So first we'll find our derivative, 5x to the 4th, 20x cubed, negative 10x cubed, negative 30x squared. Find our points, f equals 0, let's factor out 10x squared. So we'll have 2x minus 3. 10x squared equals 0, x equals 0. 2x minus 3 equals 0. 2x equals 3, x equals 3 over 2. So now we have numbers to look around. We look around 0 and 3 over 2. So less than 0, let's do negative 1. In between 0 and 3 over 2, let's do positive 1. And greater than 3 over 2, let's do positive 2. Okay. F prime of negative 1, we'll have 20 times negative 1 cubed minus 30 times negative 1 squared. 20 times negative 1 minus 30 times 1. So we have negative 50. A negative tells us decreasing. F prime of 1 will have 20 times 1 cubed minus 30 times 1 squared. So we have 20 minus 30 is negative 10, a negative decreasing. And then f prime of 2, 20 times 2 cubed minus 30 times 2 squared. 20 times 8 minus 30 times 4, so 40. Positive, increasing. So it's decreasing from negative infinity to 0, and then decreasing from 0 to 3 over 2, and then increasing from 3 over 2 to infinity. And because we're decreasing and then decreasing, there's not a max or a min at 0, but because we go from decreasing to increasing, we have a minimum value at 3 over 2. Okay, so our information here, a minimum are decreasing and are increasing. Okay, step 3. We'll analyze our second derivative. So our second derivative will be derivative of 20x cubed, 60x squared, derivative of 30x squared, 60x. Set this equal to 0. Let's factor 60x. So we'll have x minus 1. 60x equals 0, so x equals 0. X minus 1 equals 0. X equals 1. So let's look around these values. 0 and 1. We'll look at -1, half, and 2. F double prime of -1 will be 60 times -1 squared minus 60 times -1. 60 plus 60, positive 120, concave up. F double prime of a half, 60 times 1/2 squared, minus 60 times 1/2. So 60 times 4th minus 30, -15. Concave down. Second derivative of 2, 60 times 2 squared minus 60 times 2. We have 60 times 4 minus 120, which is 120. Positive. Concave up. So we're concave up from -infinity to 0. We're concave down from 0 to 1. And we're concave up from 1 to infinity. So concave up, concave down, concave up. So these are our inflection points. Let's create a sketch. First, we'll put our y-intercept 0, 0. We'll put our x-intercept 0, 0, x-intercept 2, 0. We'll put it over here. And we know we're going decreasing and concave up at 0. We switch to concave down, but we're still decreasing. We have a minimum at 3/2. So our minimum will be at x equals 3 over 2, and then it will switch to concave up and increasing. So decreasing, concave up, decreasing, concave down, minimum, increasing, concave up. Something like that. Okay, one more. F of x equals 8 e to the x minus e to the 2x. Step 1. Analyze our function. So what's our domain? Do we have any restrictions on what we can plug in for x? No, all real numbers. Y-intercept, f of 0 equal 8 e to the 0 minus e to the 2 times 0. 8 minus 1, so 7. So x is 0, y is 7. X-intercept, 0 equal 8 e to the x minus e to the 2x. Let's factor an e to the x out. 8 minus e to the x. And so e to the x equals 0, we cannot. 8 minus e to the x equals 0. 8 equal e to the x. We take the natural log of both sides. Natural log 8 equals x. So our x-intercept will be natural log 8, 0. Okay, so we have our domain, we have our y-intercept, we have our x-intercept, in this case just 1. Step 2. Analyze our first derivative. So our first derivative is, derivative of 8 e to the x is 8 e to the x. Derivative of e to the 2x is 2 e to the 2x. We set that equal to 0. Let's factor 2 e to the x. So we'll have 4 minus e to the x. And very similar to our step 1, we will have x equal natural log 4. So this is what we will look around. Our value of natural log of 4. So less than that, we'll look at 0. Greater than that, we'll look at 2. Our derivative at 0, 8e to the 0 minus 2e to the 2 times 0 will give us 8 minus 2, so 6, positive, increasing. Our derivative at 2, 8e squared minus 2e4 should give us about negative 50.08. Negative, decreasing. goes from increasing to decreasing. So we have a max. Our increasing interval, negative infinity to natural log 4. Our decreasing interval, natural log 4 to infinity. So we have our max value, we have increasing interval, decreasing interval. Step 3. Analyze our second derivative. So our derivative of 8e to the x will be 8e to the x. Our derivative of negative 2e to the 2x, 2e to the 2x, chain rule of 2, so 4e to the 2x. Set it equal to 0. Let's factor 4e to the x. So we have 2 minus e to the x. And similar to all the rest, x will equal natural log 2. Let's look around. Natural log of 2. So a number less than that, 0. A number greater than that, 1. Our second derivative at 0, 8e to the 0 minus 4e, 2 times 0. 8 minus 4 equals 4, positive, concave up. F double prime 1 is going to be 8e to the 1 minus 4e to the 2. So we'll get negative 7.81, negative concave down. So it goes from concave up to concave down. So we have an inflection here. Our concave up is from negative infinity to natural log 2. Our concave down is from natural log 2 to positive infinity. So we have our inflection, and we have our concavity. Let's sketch. So our y-intercept, 0, 7. X-intercept, natural log of 8, 0. And natural log of 8, let's see. Our natural log of 8 is 2.08. So it'll be really close to 2. We are increasing until natural log of 4 and then decreasing. Natural log of 4 being 1.4. So we will be increasing, hit our max, then decreasing. We are concave up. And then we hit natural log of 2 and we go concave down. So before we hit the max, we switch concavities. So we will be increasing and then decreasing. concave up until concave down, increasing, hit the max, decreasing. Something like that. Again, for all of these, I would double check with your graphing calculator after you make your sketch. A company estimates that it will sell N of X units of a product after spending X thousands of dollars on advertising, given by N of X equals negative 0.25 X to the fourth plus 23 X cubed minus 360 X squared plus 45,000. X being between 25 and 54, right? Those are the thousands of dollars. When is the rate of change of sales increasing and when is it decreasing? What is the point of diminishing returns and the maximum rate of change of sales? So to find when our rate of change is increasing and decreasing, let's find the second derivative and use our second derivative test. We'll take the first derivative. So we'll have 4 times negative 1/4, so that'll be a 1, negative x cubed, 3 times 23, 69x squared, 360 times 2, negative 720x. 45,000, the derivative will be 0. Our second derivative tells us we'll have negative 3x squared. 69 times 2 is 138x. Negative 720x will be negative 720. And so we can use this to find our partition. So we've got 0 equals negative 3x squared plus 138x minus 720. Let's factor out a negative 3. X squared minus 46x plus 240. Negative 3 x and x, 240, 46, 40 and 6, negative 46, positive 240, okay? So this tells us x equals 40 and x equals 6. So that's where we'll partition. So let's do, 39, 41, and we're not going to worry about less than 6 because look at what our domain is. We're only looking at values between 25 and 54. So we really don't need to worry about anything less than 25. That's not the domain we're interested in. So we'll just focus on what's around 40. So I'm going to redo this. So that way we have more room. So around 40, we'll use 39 and 41. Our second derivative at 39 will give us negative 3 times 39 squared plus 138 times 39 minus 720. Negative 4,563 plus 5,382 minus 720 is 99. Positive. This tells us concave up. Second derivative at 41. Negative 3 times 41 squared plus 108 times 41 minus 720. So we'll have negative 5,043 plus 5,658 minus 720, which will give us negative 105. So negative concave down. Okay, so the concave up at 39 is telling us that it is on the interval from 25 up to that 40. Sales are increasing over our interval, right? It's concave up. At 41, our second derivative is a negative value, telling us concave down, and so our sales are decreasing, so from 40 to 54. And our partition number, that 40, that is our point of diminishing returns. So if we plug that into our first derivative, we'll have negative 40 cubed plus 69 times negative 40 squared minus 720 times negative 40. Multiplying all of that out, we'll get 17,600. This is our maximum rate of change here. And this point the point of diminishing returns is at 40, our reflection point.